In this video, we are going to be continuing with the chemical properties of alkenes. So, and specifically we are going to be talking about addition of hydrogen halide. Hydrogen halide formula is HX, where X can be a halogen atom, any halogen atom. So, when an alkene reacts with a hydrogen halide, we get an alkyl halide. Quite easy, right? So, there are two types of alkenes: symmetrical and unsymmetrical alkenes. Symmetrical alkenes, if you see over here, now that's ethene. Now the HBr that it reacts with, the hydrogen can bind to either of these two, and the bromine can bind to this or this. Okay, and let's take case 1 where the hydrogen binds to this carbon and the bromine binds to this carbon. So this is case 1. Let me just write it there. So when that happens, our product is going to be BrCH2, okay, and CH2 and a H. The second case is going to be where bromine binds to this carbon and hydrogen is going to bind to this carbon. And that means we get this as the product. Now, both the cases, the product is 1-bromoethane. There is no change in the name or the structure. So, symmetrical alkenes basically have a symmetry across the double bond. So, in the second example over there, you have 2-bromobutane. But-2-ene. So but-2-ene has an ethyl group on either sides of the double bond. So there are 2 carbon atoms on each side. Now let's take, for example, we took this but-1-ene as the example. Then you have 3 carbon atoms on the right side, whereas only 1 carbon atom on the left side of double bond. So this is an unsymmetrical alkene. So symmetrical alkene, you do not have any issues. Either way, you get only one kind of product. So because of that, the product over here is CH3, CH2, Similarly, in this case, it's going to be CH3, this should have been CH and a CH. Yeah, CH and a H atom, and a CH with a bromine atom, and HBr. So there is not a lot of issues when we talk about symmetrical alkenes. But when we talk about unsymmetrical alkenes, in this case, you have propene. Right. So on the right side of the double bond, you have 1 carbon atom, and on the left side, you have 2 carbon atoms. So there is a possibility of 2 products. So the first one, let's assume hydrogen is going to get added to this one and bromine is going to get added there. So the product would be CH3, CH, and a CH2Br. Okay, and the other way around would be CH3, CHBr, CH2 and a H, basically CH3. So we are getting 2 products, that is 1-bromopropane and 2-bromopropane. So there is the difference that we are observing. And we need to figure out, like, how do we say that, okay, one of this is going to be the product that is going to be more preferred. So that's when Markovnikov, who is a Russian chemist, gave a generalization. What he did was, in 1869, he studied various reactions of addition of hydrogen halides in detail, and he figured this one out. So what he says is, negative part of the addendum gets attached to the carbon atom having lesser number of hydrogen atoms. When I was in grade 12, I could never remember this rule. So to simplify, basically, according to this rule, bromine will get attached to the carbon with less number of hydrogens. Because in HBr, bromine is more electronegative, so that automatically becomes the negative part of the addendum, whereas the hydrogen is positively charged. When I was in grade 12, again, I did not understand this mechanism. Now I do. So I'm going to teach that to you. So the mechanism involves two steps. And this again involves the very important concept of reaction intermediates. So first what happens is the electrophile is going to attack the alkene. And this leads to the formation of a carbocation. So when the electrophile attacks the alkene, what are we going to get? We're going to get the carbocation, and that in turn is going to tell us which is the major product. So let's take the same propene as the example. Okay, CH3, CH double bond CH2 plus HBr. Now, an electrophile means it is electron loving. It loves electrons, which means here our electrophile, the hydrogen, is going to come and attack the carbon. Basically going to come in and attack, and that is leading to the formation of the possibility of two carbocations. So, first case we will be considering is when the hydrogen atom is going to come attack, basically what is going to happen over here is the double bond is shifting to the CH2, and that will get a negative charge and it will become electron rich, and what happens is the hydrogen will come and attack the CH2 to convert to a CH3. Okay, that is case 1. So in that case, what is the product? What is the carbocation? That's going to be CH plus, it's a carbocation, and a single bond and a CH3 plus Br minus. The other thing that could happen is, I'll put that in another ink so it's clearer. So this is going to shift over here, and the hydrogen, this particular negative charge will attack the hydrogen atom. And what we'll get in this case, we will get another carbocation, obviously. And in this case, the CH2 and a CH2 with a positive charge, right, plus Br minus. So in both these cases, we are getting a carbocation. If you remember, when we studied about the stability of the carbocation, when it is attached to alkyl groups, it becomes more stable, because alkyl groups like to donate electrons. They don't want so many electrons. They're like, okay, take it, and that in turn makes sure that the tertiary carbocation is more stable than a secondary, which is more stable than a primary carbocation. So basically they are making sure that they are helping the the carbon with a positive charge to stabilize that positive charge. Okay, now in this case we have two alkyl groups, which is more than one alkyl group. So the extent of stability is higher in that case than in this one. And that is why this is considered to be more stable, and this is less stable. So always in chemistry as such, our compounds want more stability, they want less energy. So they will prefer the more stable product over the less stable product. So again, to recap, what is happening over here is the electrophile, when it gets attacked, but it leads to the formation of a positive charge on the carbon chain, leading to a carbocation. And carbocation varies with respect to the stability. When there is a more number of alkyl groups it is attached to, it becomes more stable, because alkyl groups are electron releasing in nature. That in turn will stabilize this positive charge. In this case, this positive charge is not as stable as in the first one, and that is why this is more preferred. And the next step is the attack by the Br minus ion. So what happens in this case is the bromine, we are only going to consider the stable one. So the bromine is going to come and attack the carbocation. So Br minus ion will come in and attack. Always remember, we will direction of the arrow is shows the movement of the electron always. So here this leads to the formation of a CH3, CH, CH3 and a Br. So, and if you notice the negative part, that is bromine, the negative part attacked the carbon atom having less number of hydrogen atoms. So in unsymmetrical alkenes, that's where the issue comes in. In unsymmetrical alkenes, in symmetrical alkenes, it's pretty simple and straightforward. Irrespective of where you add the HBr, the hydrogen and bromine, we are going to get the same product. But if you, in unsymmetrical alkenes, due to the fact that there's a possibility of forming two different compounds, we follow something called the Markovnikov's rule. So according to this rule, the negative part of the addendum gets attached to the carbon atom having lesser number of hydrogen atom. And this again is to do with the stability of our carbocation, which is formed as the intermediate. So when the electrophile attacks the alkene, it leads to the formation of the carbocation. And because it's an unsymmetrical, now for example, let's take in the symmetrical also. Let's assume there's a let's just assume there's a possibility of the carbocation also formed. Now irrespective of both the cases, so in this case we are taking the left carbon forming the carbocation. In the second case, we'll be taking the one on the right to form the carbocation. Both the cases, it's basically the same, and so we're not considering it for symmetrical alkenes. And the carbocation, which is more stable, will give us more product, right? Gives us the major product. And so the bromine minus ion will come and attack the carbocation to give us the alkyl halide. So with that, we're done with the addition of hydrogen halide following the Markovnikov rule. There is another rule called as the anti-Markovnikov's rule, which is basically the the opposite of this, and we'll be learning about that in the next video. So just to recap one more time, in addition of hydrogen halides, an alkene is going to react with a hydrogen halide to give us an alkyl halide. In case of symmetrical alkenes, we do not have any issues because there is a possibility of only one product be formed. So symmetrical alkenes are the ones which have a symmetry across, from the double bond. So in this case, there's only one carbon on either side. In this case, there are two carbons on either side of the double bond, making these alkenes symmetrical. There are no issues. In case of unsymmetrical alkenes, there is a possibility of the formation of two products. Markovnikov's rule states that the negative part of the addendum gets attached to the carbon atom having lesser number of hydrogen atoms. It was given by a Russian scientist Markovnikov in the year 1869 after he studied all of this in detail. So first step is by the attack by the electrophile, and when the electrophile attacks the alkene, it leads to the formation of a carbocation. And because our alkene is unsymmetrical, there are possibility of two carbocations to be formed. The one which is more stable is more preferred than the one which is less stable. The reason that one is more stable is because of the presence of two alkyl groups. These two alkyl groups will basically help make sure that the positive charge on that carbon atom is taken care of. And that in turn, there is an attack by the Br minus ion, and this leads to the formation of the alkyl halide. Also, one important thing, the order of reactivity for hydrogen halides is Hi is more reactive than HBr, which is more reactive than HCl. With that, we're done with Markovnikov's rule. In the next video, we will be talking about anti-Markovnikov's rule or peroxide effect.